Welcome to a new test and teardown video. This time it's a Tektronix 2445 150 megahertz 4 channels analog oscilloscope with all the fancy smancy digital readouts and all that. But this one is the special DMM option. See, here on top we have a digital multimeter, and I believe all the readouts and all that funky stuff here goes on the screen as well. So there's a reason why we start here on my scale, because it's what, 12.6 nearly. So it's quite heavy. It's just a fantastic Tektronix oscilloscope, and Tektronix is just one of my nice favorite brands. I always look for these on flea markets and trade-ins and swap meetings and wherever I go. So this one was the latest score, and I will check it out first. I didn't even clean it or anything. Yeah, we have a little bit of dust on it, but so far it looks quite all right from the outside. Whew, it's a little bit heavy. And what is that? I also have the big bag here of goodies. And what do you know? It's full of all sorts of... what is that? Option. We got some funky options and stuff. We also got some the DMM. What is that? Auto ranging, manual, la 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 la. All sorts of stuff here. Menu selection. All this explained here, and a little extra fuse. What on earth is all that stuff? Oh, I think that will be original probes. Let's see how many I got, and if I got the right grounding straps and all that kind of stuff. I mean, it's all original. Really? But what is that? High voltage? Ooh, that will be the high voltage probe, right? To go in here. Or is this a high voltage? It's just a normal probe? I will have to check this out. How do you operate this sucker? No clue so far. What else have we got here? Oh, look. That one. Have I really got that one? How cool is that? So this is the little screen thingy. And this way you can see what you're doing in a very bright, sunny day outside, I guess. Oh, no. So, how did I put this? Oh, okay. So this plastic here has been touched by a soldering iron, or some of these other plastic components is not compatible with this type of plastic. It looks like a soldering. Yeah, okay. Bad luck. No more goodies for today. And it is set for 230 volts. It's almost impossible to see in here, but that is always a good thing to check for. And I got a few options here, the 01 and 06 option. I'll have to go and check out what that is exactly. But first of all, I still want to inspect how is everything here, and these feet are also really good and fine. I bet that is the original cable still mounted like that. So yeah, I better open and check it out, because This one contains a lot of famous capacitors for blowing up, and I want to show you how they look like in a minute. So the first thing I recommend to check, that will be the fan. So first of all, how dirty and nasty is all this? This will tell you a little bit about the run hours of this unit, and I think this looks promising. I really don't see a super nasty, a lot of dust, and also the motor runs super nice and smooth. And also, can you hear? This is not the bearing, but this is kind of the rubber it's hanging in. See? So I think this is pretty good. I hope it's not gonna go noisy and all that. Let's start with the bottom, because that is probably the most impressive boards of them all. It's one huge main board here at the bottom, and here we got the 4 analog input channels. 2 of them, they are full featured, full speed, full division, gain, everything here. That's 2 full features channels, and the 2 additional channels 3 and 4, they don't have all the same kind of features and all that stuff, so that means it's just a much more simple thick film amplifier circuit. All those units you see here, that will be heat sinks covering up the white substrate you see down here between. If you look through the holes, you can see the white substrate. So that is a ceramic back substrate. And then you have the bare dies and bonding and all that. So it's custom chips for all the amplifiers and all that stuff. And yeah, a lot of other chips, they are made by Tektronix and custom as well. This one and also that one will be the amplifier chip. And down here driving the deflection, as you can see here. We also got the other deflection right there. And we also have, I can show you guys, can you see the little black cables through that hole? It's probably impossible to see, but that will be the delay line for the vertical amplifier, because it's an analog oscilloscope and you want to delay the vertical on the screen, so you have the possibility to trick on a leading edge and then still show the leading edge. Of course, this is the mains on-off switch. And what you want to do is move a little bit of wires and a little bit of plastic and stuff a little bit away, so nothing touches this stick that moves, because it creates all those funky sounds and probably stick it a little bit and makes it difficult to operate that switch. Other than that, everything here seems to be in a pretty good order. I don't see any leaked capacitors here, and we don't have any of those nasty RIFA capacitors on this board, but we need to look and find the power supply in here. So this is the left side of the screen. You can see the screen here and the shielding. And here we got the cathode system, and that is running minus 2000 volts. So that will be, yeah, all the cathode and the focus and all that kind of stuff. And we should probably also have a little look in there. The high voltage supply also looks really, really nice. Of course, it sucks some dust to it, but that is not so bad after all. And again, no leaked capacitors or anything. This is a custom transformer, specially made for Tektronix. And here on the top we have the digital multimeter option, and you can really see it's an option because this is the height of the normal oscilloscope. Of course, there's another special rear plate and also a special front plate. But other than that, the rest of the oscilloscope is the original size down here. And then they just added this digital multimeter here on top. I will have to take this apart and show you the internal parts of the digital multimeter as well in a minute, because I definitely need to get in here. That is where the power supply is hidden, and that is what I am hunting down. to get into that to change those RIFA capacitors. And here is the CPU on board. And look at that. Here is the CPU. It's a Motorola 67127. And software that will be in 2 EEPROMs from 95 and 94. And that is a little bit of a surprise, to be honest. I expected the software to be from like 89 or something like that. But that means this is actually not as old as I thought to begin with. So to access the fuses of the digital multimeter, you need to flip it up like that. We got 2 screws here. And when you do this, it's going to say flip. And then this cable here is going to fall out. And then you don't know where it's going. But note, there's a little white dot. And this one goes to the right side of the unit. And the 2 little pins, they are down here, hidden like that. Because there's a hidden fuse under here. And then you flip the whole board down like there you go. And now I should be able to get into the power supply in a minute. Again, a good important note. The brown wire goes to the left side here. And there isn't any indications or anything like that here. And this one could easily be mounted the wrong way. When you poke around with this for a few minutes, then you forgot all about that. Here is also a little information. There's a red and a brown. And of course the brown one goes to the fuse and the red one goes to the red one here. There's also a little chassis and it goes down there. There's actually a little surprise hidden here. So this is the control panel for the multimeter option. And that one goes here. And of course this is the flat cable for the multimeter as well. That connects to the rest of the scope. So I find it a little bit interesting. It actually goes down here and is so much integrated with the scope. I had the idea it was like a more or less like a plug-in you could take out and leave the rest of the scope, but yeah, it's a lot more integrated than I thought to begin with. This unit here is driving me a little bit nuts, to be honest. It's very, very difficult to disassemble. And it's definitely because this is not an ordinary 2445. I mean, it's because of this digital multimeter thing. All this extra stuff we got here is for that multimeter option. So we got some more software and more microcontrollers and more EEPROMs and all this stuff here is mounted on this top plate and just makes it really, really difficult to pull this up. Normally you don't have any of those circuit boards here, and then it's quite easy. So that is the fantastic power supply I wanted to get out the last few hours. I want to be sure that I can plug in everything here. We got a lot of different cables, and this one and that one, and So the power supply, to get that one out, I need to remove a few screws down here for the heatsink, and then it should be possible to pull it up. It is of course supported by a lot of little plastic, hold this here and hold this there and whatnot. I think I'm probably a lot dumber than most people, because it took me a long time to get this annoying power supply out. Oh my god. Let me show you a few things. So the cables here, they are soldered in. These are not connectors. It looks like connectors, but you can't pull them. And you can't get your fingers in there, and you can't anything when this board is in. And those two, they're like here, and they go here and here. and there's a little code pin right there, and that one is important. And also the other one, as you can see here to the left, there's also a little code pin. This one is right there. So this is what you need to be careful when you put this back in. And of course, from the top here, you can't see anything. So it's going to be real fun to plug this in again. Also, you see those two down here. And then you have two more up here, okay? So the point is the two lowest goes to the switch. And the two at the top, that's the power entry. This one is actually connected here. So I didn't need to pull this out. But it's just, I needed to do that to get room to pull and punk around with this. The fun thing is, I didn't even need to pull the power supply because you know what? They replaced the RIFA capacitors, or they're not using them anymore. See the white ones here? That is another brand that is not causing all the explosions, cracks, burns, and terror of RIFA capacitors. So somebody learned. That is fantastic. So that means in here you will find two more if you look real careful. They are hidden. Oh, I find one. But I will have to open here and have a look, and let's have a little look at this the power supply, right? Oh, inrush protection, and one more inrush protection. Yeah. Nice switch mode power supply, and down here is the transformer. Whoops! Look what I find. We got one leak capacitor. Oy. That is what we need to find. We need to do these inspections and find these components. Haha. I'm always happy that all this trouble paid off. I did find something. I'm still in the middle of the power supply visual inspection, figuring out what to do and where are we with everything. There's, the status of this thing. But definitely I want you to see a very, very alarming issue. I found a Tektronix production quality issue. Oy. You want to see? This one, the black part to the right, is not soldered in one side, and it's completely forgotten. See, the right side is fine. That one is soldered. Left side not soldered at all. So this part just goes around here, and let me try and move this. It is barely touching. See? I think I'll have to put the camera on a stand to prove this fact. Here we go. See? It's not me who made it go loose. Never soldered up here. And this one is in series with mains entry. So this will give you loose connections. How stupid is that? Oh, there's also one more little funky thing I found. So the primary side and the secondary side is connected only at one single point. You need to have a noise loop. You need to close the noise loop, and that is done by this little RIFA capacitor here. 2200, so it's 2 nano 2, and it is cracked, as you can see, all over the place. And this is of course a Y type, so that one I need to replace. And I didn't find any other RIFA capacitors, so far I'm quite happy. I've been looking all over the place. Oh yeah, the motor here is just one beautiful brushless motor. And look at all those connections here. And I believe we got some windings to control, like 2 or 3 phases. And we got some sensor phases as well. And it all comes back to this driver chip and a little NTC right there, and there you have your DC input. So this is a complete fan driver circuit. That will be the mains entry capacitors. So this is where you store your DC from your mains voltage. We got some filter components and all that stuff, and then it goes to the switch mode supply with the lead capacitor, obviously. Look at that, 0 to 40 volts. Yeah. What is that, 180 micro? Yeah, okay. So before I want to repair the power supply, I always take quite a lot of pictures of stuff like this, because we got quite a lot of different parts, and it can go wrong in the reassembly. Look at all those little metal parts, plastic parts. This plastic part here is also unique. See, there's a little thing that sticks out here, and we got these two plastic parts, and here is another little part. And this, of course, screws to the back, and it's just attached by a little pin that goes through the hole there. So all those pictures can help me remembering how to reassemble the thing again. Oh, by the way, you can see here between the two boards, there's a little metal shield, and that metal shield is also electrically connected to ground here. And the plastic holders here that holds these two boards together, as well as the screw, you need to release those using a little tweezer like this, and then carefully push the two pins in the middle towards center, but only enough until they release from the holes in the circuit board. See, they are locked like that, and don't pull too hard, they will just crack. Let's see if I can demonstrate this. It's normally super easy to do when you're doing it right, but if you push a little bit to the wrong side, it's almost impossible. So what I'm doing here is I try to get in here and then push in here. Look what I'm doing. And then just push, and then here we go. And then it's up. Oh, see? Be careful. See those thin little plastic thingies? Oy, 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 they're easy to break, right? So now I've replaced all the capacitors this size. I didn't want to replace these two because they look absolutely nice and fantastic, but it's still the same brand. But anyway, I changed all these to 220 micro, and I went all the way to 63 volts switch mode grade capacitors. So I think that's going to be all right. We got two different values, 180 and 250. So that should be perfectly fine. I also found actually two RIFA capacitors, and they are a little bit cracked, not super bad yet, but that is going to be a big problem soon. One is down there, and the other one is right here. So I replaced these two and to some new and wonderful ones. So I bet it's all going to be nice and fine, but of course we could have all sorts of other problems, and we will figure that out once I figured out how to assemble all this again. Hopefully that will be This easy. Is the digital multimeter module with the shields taken off, and even the shields, they're just fantastic. Look at the way they coated this with electric conductive, some paint or some coating like that, right? And then it goes to that screw and not the others. It's just... And the same with the bottom shield. It goes with this screw and not any other screws. Because that is a static shield, and they don't want any current to go in that shield, but it's only a static or like a capacitive noise entry shield, right? Beautiful. the whole digital multimeter module is just fantastic made. If you look at this and compare it with digital multimeters in the high price range, this is the kind of stuff you find. All those relays, and look at the Teflon standoff for high impedance, carefully trimmed current measurements, voltage measurements, scaling, and all the precision components. And look at that one. That's an LM399, a super temperature stable voltage reference as well. I did not expect that. Those are really, really expensive. And it just goes all over this. Here's the software for the meter. We got another socket for some more software. Yeah, I'm just totally impressed. Wow, look at that. The way that it's hand soldered to these components there, and to avoid leakage, it's just up in the air and on Teflon stands. Leakage isolation. Oh man. Did you expect to find all this in a meter like that? Here's another. I mean, really? So the entire oscilloscope is now completely assembled, and I dimmed the light, and now it's either a big kaboom or it's gonna work or nothing's gonna happen. I don't know. Let's try and turn on mains, and obviously nothing happens, so I need to push this button, and then 10 watts, 80 watts. That is good sign. And look at that. And then the beam is gone. 82 watts. I mean, I'm actually really, really happy at the moment. So let's try and see. We are in normal mode. I want to go in auto mode, and I enabled all 4 channels. Here we go. And here we go. Hoppa, lucky. That is one cool thing. I want to try the meter up the auto range. DC volts. Tickety. And up here it's reading the voltage. I really want to give it some voltage as well and see if that works. But that is one good. It's responding to focus. Oh, there's a nice display there, and then you can decide if you want this or that. And then you have the illumination there. I'm happy as can be. So I'm going through a little bit of testing, and I didn't really plan to make a super long video about how to test an oscilloscope because it's not super interesting. They all are tested more or less the same way, but there's a few things that is a little bit different with an oscilloscope this fast. And so the really fast Tektronix oscilloscopes, they got a built-in 50 ohm load mode here, and that is of course needed for all the very fast modes where you have a coax input, and your generator is also in 50 ohm mode because your cable is a 50 ohm impedance, so you want to do that so you can have a very high bandwidth. So at the moment I have 1 volt a peak, and I am in 200 millivolts per division. As you see here, it is exactly what I want, plus minus a few millimeters, but that is so far fine. So this is 1 kilohertz. So we will of course just crank it up here so it is the 0% and the 100% here. And then when you go down to 90 and 10, there you have your bandwidth, and then you can just see what's going on, right? So what I want to do is I want to crank up the frequency just to 10 megahertz and then dial the time base. And there we have it. It's exactly the same amplitude, obviously. So 10 megahertz, so let's take 50 megahertz. And it is, of course, still perfectly fine. I think I can actually see just a little bit of amplitude. So let's stay here. So let's just go 60, 70, 80, 90, 100 megahertz. And it is a little bit more. We see 110, 20, 30, 40, and that is 150, and then it is probably just a tiny bit. I mean, this is what they specified so far. And what else can we do? So here we go. There you have it, your 150 megahertz signal on channel 1. Isn't that amazing? So I want to show you how it works with the delay line. So this scope, of course, contains a delay line. I think I previously showed that one. So what I have right now is a 1 microsecond pulse. So if I move it a little bit in here so you can see, you can probably see this tiny little dot right here, and that is when the signal was low before the 1 microsecond pulse. And the repeat time here is 100 kilohertz, but that is not interesting. It is the leading edge of the signal that is interesting. So what happens if I dial in here, I mean zoom in on that leading edge? So we have now 10 nanoseconds per division. I don't know if you can see what's happening here from 0 to full. It's like 3 nanoseconds of rise time, and we have all this time before the pulse, and then it detects it and triggers and start the sweep and all that kind of stuff, and that is because of this delay line. Otherwise, none of this would have been possible. We can try and play with the rise time. Just for example, if I give the rise time about 10 nanoseconds from my signal generator, and we move it again like that, then the signal should go from 10% to 90%, 10 nanoseconds. So that is how it works. Let's try and play a little bit with the digital multimeter. And you can see right here we got about 3 volts of input, and that is also what my power supply say we got. So so far so good. So I'm actually a little bit impressed about this. Then we have everything here in one little go. What else can we do? It's not so fun to try and give it some more volts. This is 10. Click. Aha. So we got all this auto ranging and all that kind of fancy stuff. And the voltmeter is accurate as well. So I wanted to make a tiny little documentation about the connectivity, and I believe all we have to do is, that's difficult to show here. See, there's a little feature called connectivity. There we go. And what happens? See, and there's a very, very loud beeper, and it's really, really fast. Well, you can't really use it as a Morse code practice tool, but it's definitely pretty sweet. So I'm playing with XY mode and the original probes. I even tried to adjust them here and see if I can make the bandwidth good or anything like that. But I mean, I really think those probes are absolutely rubbish. Because look at the bandwidth here. That is not like it's supposed to look. So that is quite funny. So that's actually without probes. This is just a BNC cable connection to my little generator. And this is not good for bandwidth and everything like that. So you get those little bandwidth problems like that. So this just proves that the original probes they were just rubbish. But the scope is, of course, perfectly fine.